Good evening, students. Welcome to one more session on trees. So today we'll be dealing with binary search trees and AVL trees, right? So if you have any doubts in this session or in the session which we discussed previously, you can put your doubts in the chat box, right? Okay, we'll start off with this session. Right, binary search trees. So here in these binary search tree also you will be having good number of terminologies which you need to learn. Good number of terminologies to learn, and based on which you will be able to solve good number of problems. Right now, let us look at the formal definition, but don't worry about the definition which is given on the slide. Just try to understand what it is, right? Okay. Right. So a binary search tree T may be an empty binary tree. One second. Alright, a binary search tree T may be an empty binary tree. So this is same as your binary tree. Okay, so when we spoke about trees, you cannot call an empty tree. At least there should be one node, right? But in a binary tree, we concluded that even without nodes, you can say it is a binary tree. If you have a node which is pointing to null, you can call it a binary tree, which we discussed in last class, that is yesterday's session. So in the same way, the binary search tree also behaves. So a binary search tree T may be an empty binary tree. Okay, so you can point to a space and tell that, yeah, this is a binary search tree, right? So you can have a root node pointing to null. Okay, you can have a root node pointing to null, right? So I'll give you the gist of what is written here. So suppose if you take a node which contains a value 20, all the nodes to the left of this particular node will contain a value which is less than 20. Okay, all the nodes which is to the left subtree, which is available in the left subtree of this particular node, will be having a value which is less than 20. Okay, so I can take 10 here. In the same way, if I take a left subtree of 10, I can take 5 here. Okay, so 10 is less than 20. In the same way, 5 is less than 10, right? So in the same way, if you take the right subtree, all the values in the right subtree will be greater than this particular node. Okay, all the values in the right subtree will be greater than this particular node. So if I take 20 here, I can take 40. Okay, even if you take this node, to the right of this node, you will be having a value which is greater than 10, but you have a constraint, it should be less than 20. Okay, so only if it is less than 20, it comes to the left subtree. So you can have any values between 11 and 19 here. Okay, so for example, for this one, I'll take a value, let us take 15. Okay, you can have any values between 11 and 20 or 19 to say. Okay, so if you take 40, you can place any values greater than 40 here, and if you take this particular node, in this particular node, you can have values between 21 and 39, because 40 is here, and if you are taking any value greater than 40, it comes to this particular node. So for example, I can take 35 here, I can take 50 here, right? So the subtrees of a binary search tree should also follow these properties. So for each node u in the left subtree of V, E of u is less than E of V. Okay, so if you are taking u which is there in the left subtree of V. V is nothing but the root node or any other node. any node. Okay, so E of U will be less than E of V if it is located to its left hand side. In the same way, if you are taking a U which is there on the right hand side, then E of U will be greater than E of V. So don't jump into these definitions because you will confuse yourself. Just try to understand what is there here, right? So if you are taking root node as 20, then all the nodes which are less than 20 will be available to the left subtree of your node, and all the elements which are greater than 20 will be available to your right subtree of this particular node. In the same way, you can also consider this node. All the elements less than 10 will be available in the left subtree of 10, and all the elements to the right of 10 will be available in the right subtree of 10. Okay, so this is about binary search tree. Now, why did we, what is the concept of binary search tree? Why did we, my voice is not audible, is it not audible? Swarna is saying that it is not audible. Is there anybody else who is facing the same problem? Is it okay? Please put it in the comment box if I am not audible. Yeah, please let me know if I am not audible. Yeah, it is audible. Right. Good. Thank you so much for helping me out. So, why did we jump into a binary search tree? So, normally when we perform a search operation, we didn't cover searching techniques here yet, but I'll tell you a small thing from that particular. Suppose if you take an array and if you have elements 10, 20, 30, 40, 50, 60 and 70. Okay, let me take 7 elements available. Now, if I want to search for 50, or let me take 60. Okay, now the basic procedure of search for human psychology is normally you start searching from one element. Okay, now if there are 1000 array size of 1000, then if you want to search and in which each and every element carries the index value. Okay, suppose there are 1000 elements and first location contains 0, second location contains 1, third location contains 2 and so on. Suppose if I am searching for an element which is available at 999 location, then I should search all 999 locations from the start. Okay, which is a hectic process. So rather than doing that, you can do it using a binary search operation. So what should you do? You can perform, see, I want to search 60, right? So I can take this as my low index and this as my high index. Okay, so let me take the index values also 0, 1, 2, 3, 4, 5, 6. Okay, now I'll calculate the mid value. So what will I get? Mid is equal to low plus high by 2. Low plus high by 2, which will give you 0 plus 6 by 2, which is nothing but 3. Okay, so firstly my first search will be at 40. Okay, my first search will be at 40. Now I'll check whether 40 is equal to 60 or not. No, it is not equal to 60. Now what is 60? 60 is greater than 40 or less than 40? Yeah, 60 is greater than 40. Now what I'll do is I'll change my I'll change my low value from 0 to 4. Okay, so initially my low value was 0 and high value was 6, right? So when I found that 60 is greater than 40, then what I'll do is I'll update my low value. Low value will be mid plus 1. Okay, mid plus 1. You already compared your value with mid, and you are very sure that yeah, mid is definitely not your key element which you are trying to search for. So what is the mid value? 3. So 3 plus 1 will be 4. Now you will again search. So you again calculate mid with the new value of low. So 4 plus 6 by 2. It is nothing but 10 by 2 is equal to 5. Right? So when you check the index 5, yeah, 60. I got my 60. I am searching for 60. So how many comparisons did you do? Just 2 comparisons. You just did 2 comparisons. But if you're trying to do it in linear search, then you need to start comparing from your first location to all the way to till the end, if your value is located at the end. Okay, if your value is located at the start of the location, start of the array, then you can directly find the value with less number of comparisons. But if it is located to the end of the array, then it would take more number of comparisons, right? But there is a constraint for this binary search tree. Suppose to perform linear search, I can give the value something like this: 19, 85, 20, 11, 2, 6. Okay, so this is neither in ascending order or descending order. You can perform linear search on this, but you cannot perform binary search on this, right? You can perform binary search on the array only if it is sorted. Okay, you can perform binary search on the array only if you feel that it is sorted, right? If you are not sorting it and performing binary search, then definitely this rule will not work out, right? So for performing sorting, you will take some time. Rather than, it would be better you feel that, okay, I will do my linear search, right? Now the concept of sorting is taken out from this binary tree when you are constructing a tree. Okay, let me take the same list of elements: 19, 85, 20, 11, 2 and 6. We can construct a tree from this. Okay, I will tell you about construction of trees, but if you have any doubts, put it in the chat box. Any doubts? Why are we comparing with 60? Because 60 is the key element. We wanted to search for 60. See, I have a list of array elements and I am searching for key. I am searching for 60, right? I am trying to find one element out of the set, 60. You can also compare with 10. With just one comparison, you will get your 10, right? So I am trying to tell you the advantage of binary search, right? So when I take 60, if you perform linear search, you will be comparing with each and every element from here till here. So how many comparisons did you do to go till index 5? You did 6 comparisons, which means that starting with index 0. But if I am doing the same thing with binary search, I did just 2 comparisons. Okay, I hope you understood this. So try to understand what is binary search tree. If you have a node which contains a value, all the elements to the left of this node will be less than this node, and all the elements to the right of this node will be greater than this particular node, right? Right. Okay, if I have equal nodes, then what is the case? Can somebody answer? I'll give you the answer if you give me a wrong answer. Okay, if the nodes are equal, I told that it is to the left you have less than 20, to the right you have greater than 20. If I have two 20 nodes here, then what should I do? 2 nodes with value 20, what should I do? Or 2 nodes with value 10, what should I do? Put me the answer. Alright, so binary search tree follows the following norms. All keys of the binary search tree must be distinct. Okay, so if you have nodes which are repeated, you can definitely say that it is not binary search tree, right? All the nodes in your binary search tree should be distinct. Okay, that is the answer for the previous question which I asked you. So all the keys in the left subtree T are less than the root element, and all the keys in the right subtree T are greater than the root element. Okay, the left and right subtrees of T are also binary search trees, the same thing which we discussed previously in simple terms, right? So I have taken alphabetical sequence A, B, C, so on till Z, and then if you take G as the root, B and E comes to the left part of this tree, and M, K, I, Q, Z comes to the right part of this tree if you are trying to construct a binary search tree with this particular set. Okay, so you can see that E is greater than B, hence it is falling to the right subtree of B. In the same way, you can assume what is happening with the other nodes. Okay, right? You want me to tell you how to write code? Okay, fine. Okay, what I'll do is, so what kind of code you want? You are good with the concept? Everyone okay with that? Okay, I want to perform an insert operation, right? So how do you perform? Suppose I'll take a list of numbers here, 10, 18, 25, 16, 19, 22. Okay, now I want to create this, right? So initially the first element which I took was 10, right? Next I want to create 18. So you compare 10 with 18 and find that 18 is greater than 10. You place it onto the right subtree because 18 is greater than 10. Next you have 25. You compare 25 with 10 and then you find that it is not equal to 25 and 25 is greater than 10. You jump to the right subtree because it is greater. You compare 18 with 25 and find that 25 is also not equal to 18 and it should be greater than 18. So you will be placing your 25 here. Okay, I'll take one value which is less than 10 also so that you can find a balancing somewhere. I'll take 9. Right. Next 16. Where will 16 come? It should be greater than 10, less than 18. Okay, 16. 19. Where will 19 come? Greater than 18, less than 25. You have 19 here. 22. Greater than 18, less than 25, greater than 19. 22. Coming to 9, it is less than 10, you will place it here. Okay, so now how will we write linear search, binary search, and today's topic? Linear search and binary search, you have a separate session for linear search and binary search, right? And if you want me to write code for this one, yeah, and I'll do it for today's topic, right? But we have good number of MCQs. But before that, okay, I'll give you code for this. So I hope everybody understood what we did here. Okay, I hope everybody understood what we did here, how we perform the insertion operation. Right, now in order to perform insertion in a binary search tree, what we require is a node. Okay, so if I am trying to insert node 10 or if I want to insert 10 into a binary search tree, I need to create a node first, right? I need to create a node first. Right, so let me write a function insert and I am passing the node value here. Let me take struct node star, let me take node 1 or you can say temp node. Okay, temp node. So what I am trying to do here is, initially my root node will be pointing to null. Okay, you know what is the structure, right? The structure will be something like this, which can store two addresses. You can call this left, you can call this right, and you can call this key. Okay, you can call this key element, right? Now once I want to insert this temp address into one of these, right? So I'll check if my root is equal to null. So when root is equal to null, which means that there are no nodes available. Okay, there are no nodes available. So initially my root is null, so there are no nodes available. So what I'll do is I'll initialize or I'll assign this temp address to this particular root. So root is equal to temp. So I'll tell you what is happening exactly. So suppose take root is equal to null. Okay, so I can call this as a binary search tree because you are pointing to null. Now I created one node. Okay, I created one node which contains a value 10 and I gave a name temp to it. Okay, I gave a name temp to it, right? So as root is pointing to null, what I'll do is I'll initialize the address which is there in temp into root. So initially temp was pointing to this. Also root also will be pointing to this because you have initialized root with temp. Root is equal to temp. Okay, so the address which is stored in temp will also be stored in root, and root now will be pointing to this particular node. Okay, fine. Now let me insert one more node, 18. Okay, so this time when I'm trying to insert 18, I'll create a node. Okay, I'll write here. I'll create a node which contains 18, and you have null here and you have null here. Okay, and this has a name temp. So this is no more a temp now. Okay, now I'll check if root is equal to null. No, root is not equal to null. Now what should I do? Else, if I need to check the value which is available in temp key with the value which is available in root key. Okay, so if temp hyphen key is less than root hyphen key, right? If temp hyphen key is less than root hyphen key, what should you do? Okay, this is greater, right? So first we'll write condition for greater. Temp hyphen key is greater than root hyphen key. What should I do? Now I need to insert this to the root part, right? So what I'll do is I'll call a recursive function of insert again. So this insert will have a return type. 1 second, I'll try to write this in a, okay, I'll just rub this off. Struct node star is the return type of insert. Okay, and insert will have an argument struct node star temp, which I am calling. So I'll just rub this off so that I'll save some space. So inside this I am calling if root equal to null, then root equal to temp. Okay, now else if temp hyphen key is greater than root hyphen key, if temp hyphen key is greater than root hyphen key, so I have written the same thing here just to save space. Okay, now what is happening here? Temp hyphen key is 18. You compared with root hyphen key and found out 18 is greater than 10. Now what you need to do is you need to assign some value to this root hyphen left. Okay, so root hyphen left equal to the return address of insert of okay, 1 second, you also need to pass an argument of struct node star root. Okay, now insert of the value which I need to add it to it, which is nothing but temp, okay, comma root hyphen left. Now try to understand this. So what is happening here? When I call root hyphen left, I am trying to place something here. Okay, I am trying to place something here. What will get placed there? When you call insert of temp comma root hyphen left, what will be the values here? Can you guess? So you are calling insert of temp. Temp is nothing but this one. So I'll say that address of 18. Okay, this one, same thing, temp, comma, what is there in root hyphen left in the root node? Initially there will be null. Okay, initially there will be null, right? So when you are calling root hyphen left, null will be passed here. Null will be passed here. So when you go into this particular insert, what did you write? If root equal to null, what should you do? You need to assign this temp to this root. So the temp which we created will be assigned to this particular root. Okay, and at last, at the end, before you close this particular function, you need to return root. Okay, so when you're trying to return it, when you return it, what happens? The address of this particular temp will be stored into root hyphen left. Okay, so the address of temp will be stored here, and the connectivity would be something like this. Okay, you will be having null here, you will be having null here. Okay, any doubts? Yeah, place it in the right side of the root. Now, in the same way, can you guess what can happen for the next else? Else, it will be, so if it is not the temp hyphen key is greater than root hyphen key, this is the condition. If it is less, then I need to write that condition. So it will be root hyphen right is equal to insert of temp comma root hyphen right. Okay, yeah, before you close this, you need to return the root and then you need to close it. Okay, so this particular concept will definitely work for any big array. Okay, so let me give you an example. I want to insert, see, for this particular tree, I want to insert, let me take 654. Okay, let me try to insert 655. Okay, 655 is what I am trying to insert. Initially, I will call insert of address of 655 comma root. Okay, what is root? Root is pointing to 416. Okay, so I say address of 416. Right? Now, inside this particular function, when I perform the comparison, I find that 655 is greater than 416. So if it is greater, what should I do? Temp hyphen key is greater. Yeah, this should be right. I'm sorry. Temp hyphen key is greater than root hyphen key. Temp hyphen key is greater than, this should be right. This should be right because you are inserting to the right part. Okay. In the same way, this should be left. This should be left part, right? So this should be left part. So when you are calling this, what will happen? You will be calling in order again, okay, with respect to the address of your right node. So what is the address available in right node? It is the address of 891. So it will call address of 655 comma address of 891. Okay, now you compare 655 with 891, you will find that 655 is less than 891. You will again call in order of address of 655 comma 891's left node because it is less than left. 655 is less compared to 891. So it will call this node. So this will be my new root. So it will be address of 465. So likewise it will go all the way down until it finds a null value. Okay, so once it finds a null value, it will return, it will initialize that null with the value of temp and then return it back. This statement is very much required because only with this statement you will perform the connectivity of the node. Okay, anybody having doubt with the insertion, please let me know so that I can explain it to you again. Yeah, you can take the arguments as temp comma root, but when you are passing it, you need to pass what are the parameters. Okay, you can pass, you need to, Okay, directly temp and root, it should be address of temp. If it is address type, you can directly pass it, but as you are defining the function, you need to declare with its data type. Okay, is it okay? All right, we'll move to the next one. So the insertion operation and search operations are both same. Insertion operation and search operations are both same. So you try to perform a search operation. If you end it onto a null node, if you end it to a null node, you can say that element is not available. If you end it onto some internal node, you can say that element is available. In the same way, if you want to perform an insertion, you would be doing the same process which I explained. Okay, right? Okay, next. So search operation, as you said, you don't require theory. I'm just skipping it. Deletion of a node from binary search tree. Yeah, this is something important. You understand the concept here? Do you understand the concept here? Should I tell the concept or directly the code? Please let me know. Okay, I'll start off by then put it in the comments. I'll follow. So firstly, we need to search the node which we want to delete. Okay, once we find the node, there are three cases. The node which you find might be a leaf node. The node can be can have no siblings to it, which means that it is the only child of that parent. Okay, in the same way, it can have both left and right subtrees. It can have both left and right subtrees, right? So I'll tell you a case here. Okay, I have examples here for you. Yeah. So this is case 1 where I'm trying to delete a leaf node. So look at this particular tree, binary search tree. I want to delete 333. So 333 is the leaf node. Okay. So there are no nodes connected to 333. So you can directly delete it. That is, disconnect this from this particular tree and free this particular memory location. The deletion is very simple here. You can directly delete it. Okay, you just have to disconnect this particular node and delete this particular node, right? That is the only thing which you do in case 1 where you are looking at, you are trying to delete a leaf node. You are trying to delete a leaf node, right? Second case is that if you want to delete a node which has a single child, okay, it can be either left child or right child, but it has only a single child, right? So if you take here, you have only examples of single child here. 111 has single child, 345 has single child. In the same way, 456 has single child and 765 has single child. So here in the example, he tried to delete this 891. Okay, so the 891 which was deleted, it would directly link this with its child. Okay, 891's child would be linked to 891's parent, right? That is how you delete this. Okay, now coming to the third one where I have two nodes. Okay, so 416 here I am trying to delete this 416 which has two children. Okay, which has two children. There are two choices for you. First one, you can replace this node with in-order predecessor. That is, if you are trying to represent this tree in order, you can replace this value with the value which comes before this. Okay, which comes before this. So definitely that value will be in the left subtree, or you can say that greatest value in left subtree. Okay, so you can replace this node value with in order predecessor, or not both, right? Or you can replace this value with in order successor. you can replace this value with in order successor, right? So you can say that least value in right subtree. You can say that least value in the right subtree. Okay. Now what did he do here? So for the example which is given here, 461 was replaced with 456. Okay. So you can say that 456 is the least value which is available in the right subtree. So if you take the right subtree, 456 is the least value which is available in the right subtree. So you replace this value here. Okay, you replace this value here. So this value, instead of 461, it will become 456. And call a delete function. Call a delete function of this particular node 465 in this particular subtree. So what will happen? So you are trying to delete a node which has a single child. So what will happen? This will become the root node. Okay, this will become the root node. So 465 comes here and this root node will be connected to 765. So this is what happened here. So this is the case 2 I was talking about. Let us go ahead with case 1. Okay, so what to do here? What is the greatest value which is available here? What is the greatest value which is available here? It is 345. Okay, for 345 is the greatest value available here, right? Now replace 345 with the root. So 345 is my root. Okay, now in this particular subtree, try to delete 345. So this is nothing but case 2 where 345 has only a single child. 345 has single child. So what happens here? The right part of 111 will get connected to 256. Right part of 111 will get connected to 256. So what will happen here? You will be having 111 here, and to the right of 111 you will be having 256, and here you have 456 and then 765, and to its left you have 654. Okay, understood? So you can either do this or this. Both are okay, both are correct, because by the end of deletion these two should become a binary search tree, right? So you can see that this is also a binary search tree, this is also a binary search tree, right? So this is how deletion happens. So deletion are in 3 parts. If you want to delete a leaf node directly, you can delete it right away. If you want to delete a node with a single child, then directly connect the deleted node's parent with the deleted node's child, directly connected. Okay. In the same way, if you are trying to perform a deletion of node having 2 children, then you need to perform this process. Either this or this. Okay, not both. Don't do both, do only one. Okay, write code for only one. Right? Understood? Okay, now I hope with respect to yesterday's class and today's class, you have understood what is a tree, what is a binary tree, and what is a binary search tree, and their differences between them. So you also can know the advantages of binary search tree, because you can perform searching faster, right? Now, drawbacks of binary search tree. If you are taking a skew tree, then normally when you take binary search tree, the performance of search, suppose if you have n elements in your binary search tree, then on an average, if you are trying to search for an element, then it will take order of log n time. Okay, it will take order of log n time, right? But if you are taking a tree something like this, see, this is a binary search tree and this is also a binary search tree. Okay, if there are n elements here, that if you want to search for m, it will take order of n time, because even though it is a binary search tree, the tree is not completely balanced. Okay, the tree is not completely balanced. That's the reason why we have a problem with the binary search tree, or the binary search tree's advantage we are unable to make use of it, right? So because of this drawback, we have something known as AVL trees, okay, which we'll see. So before we jump into the AVL tree, let us go ahead with a few MCQs. Yeah, can you give me the answer for this? Can you give me the answer for this? See, one best thing which you can do with this is try to draw the tree. Okay, suppose we have numbers between 1 to 1000 in a binary search tree and want to search for a number 363. Which of the following sequence could not be the sequence of node examined? Okay, so out of these set of sequence, which is the wrong sequence? That is what he is trying to ask, right? Now let us start drawing a tree here. So let me take 2, the first one. So 2 is greater, so 252. Next 401, yeah, 401 will come here. 398, so 398 will come here. Okay, 398. 330, 330 will come here because it is less. 344, yeah, it will be greater. 344 and 397, 397, and then 363, 363. Yeah, this is correct. Okay, nothing wrong with this, right? Now let us go with the second one. 924. So 924's left child, you'll be having 220. Okay, you are understanding how I am taking this to the left, right? 220 is less than 924, hence I am taking to its left. 911. Okay, next 244. Next 898. Next 258. Next 362. Next 363. Yeah, this is also correct. No issues, right? Next 925. To its left you will be having 202. To its right you have 911. Next to its left you have 240. Next you have 912. See, look here, 911. So in 911's left subtree, you should have all values which are less than 911, right? But you are getting 912 here. So this is the patch. Okay, so if you look at any other nodes, see, if you look at here, all the values here should be less than 398. Okay, all the values here should be less than 398. If you take here 401, all the values here will be less than 401. If you look here, all the values here will be greater than 330, right? So this way you should make your caution, ensure that all the values are in between a particular range, right? So the answer here will be C, because you cannot have 912 to the left of 911. Okay, you cannot have 912 to the left of 911. Let us also check this D. 2 and 2 is greater, 399, 387. So 387 will come to the left, 387, and then 219 to its left, 219, and then 266 to its right, 266, 382, 382, 381, 381, and 278, 278, and 363, 363. So if you look here, all the values here are greater than 382. In the same way here 266, 266, yeah, you can take this because it is left child, right? 266, all the values here are greater than 266. So this is correct. So the wrong one is this one, C bit. Okay, so nobody gave me a correct answer. Yeah, only one gave me a correct answer, right? So next one, right? In full binary tree, Okay, right. One more thing which I want to tell you about full, complete, and perfect, which I told you yesterday, right? So make sure that you don't lose marks here, because in the textbooks which we refer, normally BTech people refer, we only study full and complete. Okay, so what we study with full is something like this one: all leaf at the same level, and complete means it should follow the sequence 1 2 3 4 5 6 7 8 9, so it should follow the sequence which is complete. Okay, that is what normally if you are learning a BTech, referring to a BTech book, it will tell. But if you refer to Wikipedia, if you refer to wiki, this has a different definition. Now it is not about who is correct and who is wrong. Okay, don't worry about who is correct and who is wrong. Try to ensure that you give a correct answer when you are trying to answer it in an interview or a objective paper. Okay, now in an objective paper, if it is referring to only these two and the concepts of only these two, don't look into this. Okay, don't even have a thought of this one. Okay, if he's giving a question in terms of only these two, keeping in mind only these two, and there is no concept of a tree having zero child, a tree having all nodes in a tree having zero child or two children, if there is no concept of that one which I told you about full binary tree, if there is no such concept there, then don't worry, stick to your BTech. Okay, if he asks you something about perfect binary tree, then only jump to this particular concept. Okay, don't give a discussion there. He has given like this here, he has given like that there. Don't jump into that particular discussion. All what you need to do is you need to crack your interview or crack your objective paper. For that, make sure that you only stick to the basics, right? So if it is asked only with regard to full and complete, you can take this, right? But if there is a word perfect, or if there is a word asking for a tree which has only 0 children or 2 children for each and every node, then you need to take perfect into consideration. Okay, so you can refer to this wiki, searching for trees. Okay, trees in data structures, you can search for that and then have a look at it, right? But if you are looking for regarding this in a normal textbook which you are referring in your BTech, then you will be having only full and complete. There is no perfect here. Okay, there is no perfect tree, binary tree here. Okay, now can somebody tell me the answer for this one? I've already got good number of answers. 49, 25. Oh my god. Why? So, okay, take the full binary search tree, right? So, when you're taking binary search tree, take it in terms of BTech and tell me the answer. Take it in terms of BTech and tell me the answer. You have already learned a formula yesterday. You have already learned a formula yesterday. So this is the full binary tree which I am trying to consider. Okay. Now, can somebody answer? There are 100 leaf nodes. So look here, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 leaf nodes. Okay. How many internal nodes are there? 1, 2, 3, 4, 5, 6, 7. If there are 100 leaf nodes, how many internal nodes are there? The answer is 99. The answer is 99. Okay? No. Yeah, sorry. So, leaf nodes will be higher. So, I am talking about internal nodes. Okay? Leaf nodes will be higher. 100. See, 8 leaf nodes, you will be having 7 internal nodes. Okay? So, I am talking about internal nodes. So 100 leaf nodes, 100 minus 1, 99 internal nodes. Okay, so please keep this in mind when you're trying to solve problems. If there is a reference to perfect, then follow this. If there is no reference to perfect, follow this. Right? Okay, next one. I hope you can answer this very easily. I hope you will be able to answer this very easily. Which type of traversal of binary search tree outputs the value in sorted order? Let me take an example. 99, 112, 76, 80 and 50. Yeah, I already got some answer here. Option is, oh my god, no. Yeah, in order. See, in a binary search tree, the in order gives you nothing but the sequence of elements. So if you take, how will you calculate in order? Left, center, right, right? So firstly you go to left, here also left, center, right. You go to left, you find that left is 50, then you track your center, it is nothing but 76. Next your right, it is nothing but 80. You come back, tell that center left is over and traverse the center, which is nothing but 99, and then go to right 112. This is nothing but in order. Okay, so outputs the value in sorted order. So this in order gives you the value in sorted order, right? Okay, next question. If a node having two children is to be deleted from a binary search tree, it is replaced by its, yeah, we have seen this. What is the answer? Yeah, good. So what is the answer for this one? We have already seen this. So what is the answer for this one? So the answer for this one is in order predecessor and in order successor. Okay, you can either do anything, right? So you can say both A and B. You can replace the node to be deleted with its in order predecessor or in order successor. Okay, both A and B, right? Okay, the runtime of traversing all the nodes of a binary search tree with n nodes and printing them in order. Okay, so if you want to print them in order, you need to traverse into each and every node, right? Now, what is the time complexity for that? What is the time complexity for that? So normally there are students who directly jump into conclusions where whenever they find a binary search tree in the question, they directly go for the option log n. Okay, but this is not the case here. It is because if you want to traverse each and every node, it should visit each and every node, because traversing. Okay, traversing, because I need to print all of them, so I need to visit each of them. So if there are n nodes, then the time complexity is order of n. Okay, time complexity is order of n, right? So that's what I'm talking about. There are a good number of students who gave me a D as the answer, but try to understand the question. Even if it is a binary search tree or normal tree, if you want to traverse them, if you want to traverse all the nodes of the binary search tree, then you need to go with order of n. Okay, if you want to search for a single element, you can say it is okay order of log n. Okay, if you want to search for a single element, you can say it is order of log n. But if you are traversing all the nodes, then it should be order of n. Okay, right. Next, yeah, can somebody answer this? A binary search tree is generated by inserting the order of the following integers. A binary search tree is generated by inserting in order the following integers. So you need to construct a binary search tree for this. So before I construct, I expect you to answer it. Okay, let me construct it. I require the number of nodes which are available in the left subtree and right subtree, okay, respectively. So this should be the left subtree, number of subtrees in the left, and or number of nodes in the left subtree and number of nodes in the right subtree. So the root is 50. So 15, it comes here. Next 62, yeah, I'll construct it here because it is greater than 50. 5, it will come here. 20, so it comes here. Next 58, so 58 should come here. Next 91, 91 would come here. Next 3, 3 would come here. Okay, 8, so yeah, 8, 37, so it is always here, 37, 60, 60 less than, yeah, greater than, and 24. So if you are looking for 24, then it is something like this, 24. Okay, so 1 2 3 4 5 6 7, yeah, 7 left, 1 2 3 4, right? So this one is the answer. Okay, so you should know how to construct a binary search tree. Option A, no, left and right, right? Left subtree and right subtree. Yeah, option B, right? Yes, good number of answers and everyone correct. Alright, let us jump into AVL trees because we have half an hour and we need to complete it. So AVL trees. So AVL came from the name of the persons who invented them, Adelson, Welski and Landis. It is better if you have a bit of idea on that, right? Okay. Now AVL trees, as I told you, was designed because of the disadvantages of binary search tree, the AVL tree follows the concept of balancing. Okay, AVL tree follows the concept of balancing. So there are few operations here. Few operations are, okay, I'll directly jump into the concept. Okay, so AVL tree, what you can perform in an AVL tree is you can perform insertion, you can perform deletion, and you can perform searching, SEARCHING. Okay, so same thing which you are doing with binary search tree, you will be doing it with AVL tree also, but you will not get a tree like skewed tree in AVL trees. Okay, you will not get a tree like skewed tree in AVL trees, right? Now let me tell you about searching procedure. The searching procedure in AVL tree is same as the searching procedure available in binary search tree. You search for a particular node, and if that node is less than the node which you are trying to search for, you need to search it in the right subtree. If it is not, you need to search it in the left subtree. The same searching procedure which we did previously, so you don't have to worry about searching. Okay, and in this class I don't want to deal with deletion because deletion is not asked in, I didn't find any questions of deletion in AVL tree. The worst which they asked for is the balancing factor, which I want to tell you when we are doing insertion. Okay, now let me take a list of numbers. So 10, 20, 30, 40, 50, 60, 70, 80. Okay, let me take this list. Now if I am trying to construct a binary search tree from this list, you will be getting something like this, right? 10, 20, 30, 40, 50, 60, 70, 60, 70 and 80. That is, you would be getting a skewed tree. Okay, you got a right skewed tree here for the kind of input. Okay, now let us do the same thing with AVL tree. Let me do the same thing with AVL tree. So I want to create, okay, firstly there are no nodes, I'll create 10. Next I'll insert 20. Okay, now after inserting each and every node, try to calculate the balancing factor of that particular node. Okay, so what is the balance factor, or what you can say, once again, yeah, balance factor. So balance factor is nothing but the weight or the height available in the left subtree minus the height available in the right subtree. Okay, the height of the nodes which are available in the left subtree minus, so balance factor is equal to height of nodes available in the left subtree minus height of the nodes available in the right subtree. Okay, just look at here. So number of nodes available in the left subtree, you have 0 nodes, so you can say height is 0. Number of nodes available to the right subtree, nodes, there are no nodes, so you can say height is 0. 0 minus 0, you can say 0. So 0 is the balance factor of 20. Okay, in the same way, look here, number of nodes to the left subtree, it is 0. Number of nodes to the right subtree, you have 1 node and its height is 1. Okay, its height is 1. So you can say that the balance factor of this node is, minus 1. Okay, I'll draw it here again because I want to insert the next value. So 30, I want to insert 30. So 20, next I'll insert 30. Okay, now when I try to insert 30, what is the balance factor of 30? 0, because there are no nodes. Okay, balance factor of 20, to the left you have 0 nodes, to the right you have 1 node and its height is 1. So it is 0 minus 1, which will give you minus 1. Okay, balance factor of 10, 0 nodes, height is 2, which means 0 minus 2, which will give you minus 2. Right? Now in AVL trees, if you have you can only have balance factors of nodes 0, plus 1 and minus 1. Okay, if it doesn't have the balance factor anything other than these 3, then you need to perform rotations. Okay, you need to perform rotations on this. So there are 4 kinds of rotations here. I'll just deal with the rotations first. Yeah, there are 4 kinds of rotations in an AVL tree. First one is left rotation, left right rotation, right rotation and right left rotation. Okay, left rotation, left right rotation, right rotation and left rotation. Please understand this. Left rotation means you are rotating towards right. Okay, the position of your nodes will be something like left. Okay, so this is nothing but LL rotation, which means that you are rotating towards right. So what will happen here is you are trying to rotate this particular node to the right, which means that B node becomes the root node. Okay, B node becomes the root node. So that is about rotate left. So you have LL here, which means that LL rotation, right? So in the same way, you can guess RR rotation. Look here, you have RR, you rotate to the left part, you rotate left. Okay, which will give you this particular tree. The tree which was like this would be transformed like this. So what is the significance of rotation? So initially you can tell here, so this is the same kind of tree which we were dealing with. So you had a balance factor of -2, -1 and 0. After you perform the rotation, look at the balance factor. This is 0, this is 0 and this is 0. Right? So you made sure that the tree is balanced, so that anytime you search for a particular node, you can get the node in order of log n. Whatever may be the kind of nodes which you are trying to insert, you will get the node in order of log n time. Okay, so that is the advantage of AVL tree over binary search tree. Look here, left right rotation. So you have an L, you have an R. So there are 2 kinds of rotations here. Firstly, you rotate this B or this particular set to the left first. So it will transform to this particular node. and then here you need to perform a rotation towards your right. So this is called left right rotation. Okay, firstly you rotate to the left, the bottom part, where this is the node where you need to rotate, right? Not this node. You need to rotate this node, and for right you need to rotate this node, right? Okay, in the same way you can see that right left rotation. So RL, so first you need to go to the right and then to the left, so RL rotation, right? So firstly you rotate to the right, and then there once you rotate to the right you will get RR, hence you perform rotation to the left. Okay, so this is something like, see, this left right rotation is something like, you assume that there is a node here. Okay, so this is nothing but RR rotation. You are performing an RR rotation here and then an LL rotation, right? So you are mixing up these rotations. You are trying to perform an RR rotation and then an LL rotation, right? In left right. Here also in right left you are performing an LL rotation. Assume that there is some node here, so you are performing an LL rotation and then RR rotation. Okay, so that is about rotation. So let us jump back to the question which we are dealing with. So here you have, so what rotation should you do here now? Answers. What rotation should you do here? What rotation should you do here? You need to do an RR rotation. Okay, you need to do an RR rotation, RR. So it will transform to 20, and then you have a 10 here, you have 30 here, so which will ultimately make the balance factors 0. Okay, now try to insert 40. Yeah, I want to insert 40 here. Look at the, okay, I'll insert it in a new node, as a new node. So 20, 10, 30 and 40. Okay, so look at the balance factor. This is 0, this is minus 1, and what about this one? 20, 1 minus 2. 1 minus 2 is nothing but minus 1. So there is no imbalance here. Imbalance will happen if it has balancing factors other than 0, plus 1 and minus 1. You have minus 1s here, so there is no great problem. So next I'll try to insert 50. So 20, 10 here, you have 30 here, you have 40 here, and then you try to insert 50 here. So what happened? You have balancing factor 0, minus 1, minus 2. This is also minus 2. Okay, so you need to perform an RR rotation for this particular node, because the balance factor was affected to this particular node, so I need to perform a rotation at this particular node. So what will happen? 20. When you perform the rotation, it will be 40, and 30 will come here, 50 will come here, and then you have 10. Okay, look at the balance factors. 0, 0, 0, this is 0, and this is 1 and 2, minus 1. Fine, right? Next I want to insert 60. So 20, 10. So when I am doing this, you will only get, see, 60 gets added here. You will only get right rotation here. Okay, I'll give you one more example where you will be getting better rotations, right? You will be able to know all the other rotations also. Okay, I hope you have understood what are the rotations happening here, why we are rotating, and if we rotate, what will happen, right? So I hope everybody understood this. I'll take one more example. So in order so that it doesn't create a left skewed tree or a right skewed tree, we are going for rotations. Okay, good. Now let us jump to the example. So these are left right rotations. So this is the example which I want to tell you here, which I just created for you to understand what are rotations. So initially I took only node 50. So empty tree, I created a node 50. And then I tried to insert a node 20. So 20 got inserted, and I have represented their balance factors in brackets. Okay, so 20 is less than 50, so I represented 20 to the left of 50, and there is no problem with the balance factor because balance factor is 0 and 1 only. Okay, right. Next, I want to insert 60. So 60 comes to the right of 50, and balance factors you can see all are zeros. Next, I want to insert 10. So when I insert 10 here, you can see here balance factor is 0, this is 1, and this is also 1 because it has one node here. Okay, so no problem of rotations coming here. Now here I am trying to insert 8. So when I am trying to insert 8, look here, you have balance factor 0 here, you have balance factor 1 here, I got a balance factor 2 here, which means that I need to perform a rotation on this node. What kind of rotation will you perform here? So you are going to left and again left. So you need to perform LL rotation, which is nothing but rotate right. Okay, LL rotation is nothing but rotate right. So you perform a rotate right where this 10 will become the root node and 8 as usual is the left node and 20 will become the right node. Okay, and look at the balance factors, both are zeros, this one will become 0, and if you look at the balance factor of 50, it is 1 because the depth is 2 and the depth is 1. Don't worry about the balance factor here. What is the balance factor of this one? 1, 2, 3. 3 minus 1, it should be 2. Okay, so this is before rotation, right? After rotation, look at the balance factor, it automatically changed, right? So this is wrong here, it should be 2 here. But when you are trying to do this, so when you say that, okay sir, there is an imbalance here, there is also imbalance here, you need to rectify from the bottom. Okay, don't say that sir, I will first rotate this and then I will rotate here. No, once you rotate this, this will automatically get balanced. Okay, that's what we have seen here. Okay, but if still imbalance occurs here, you should rotate this also. Okay, right. Next, I am trying to insert one more node. What is that node? After 8, 15. Okay, so I wanted to insert 15. So 15 will be in between 10 and 20. So it will be the left child of 20. So left child of 20. So look here, look at the balance factors here now. 15, 20, 10, 50. So balance factors 0, 1, minus 1 and 2. Okay, and 60. So the balance factor is 2. So there is an imbalance which occurred here. Now what rotation should you do now? First one is L, that is correct. Not this one, because the imbalance occurred due to this node. Imbalance occurred due to this node. So it comes from your right. So you need to perform LR. Okay, understand? Because imbalance occurred because of insertion of this node. So this node is available to the right of this 10. So you need to perform LR rotation. Rotation should be performed at this node, and from this node you need to look at the direction in which the newly inserted node has been done. So you need to perform an LR rotation. So firstly you need to perform an RR rotation and then you need to perform an LL rotation. Right? So look at this. So initially you would be performing okay, I'll write that intermediate step for you here. So you need to perform an LR rotation. Assume that there is a node here. Okay, so you have 50 to its right. You are performing an RR rotation. So this will become the root. 20 would become the root. Okay, so 20's left child will become 10. 10's left child will become 8. Okay, what is 20's right child? So 20's right child is null. Now what about this 15? What will happen to this 15? This 15 will get connected to this particular 10. Because 10 initially had 2 children. But when I rotated this, 10 has only one child. Right? And the child of 20 will go to 10 because 20 has 2 children here. So 1 is the null which we represented here. This is what I am representing it here again. Okay. Now you need to perform a left-left rotation. So when you perform a left-left rotation here, what happens? 10 goes to the root Okay, 10 goes to the root. Yeah, left rotation here on this 50, right? So 20 goes to the root. Okay, and 50 comes as a child of 20, and 10 has two childs, 8 and 5, the same thing which we saw, right? And 60, which is connected to 50, stays there. Now look at the balance factors here. You have -1 here, you have 0, right? So it has been balanced. Okay, understand? Next, I want to insert 32, so I can directly insert 32 without any performing any rotations, because you have a vacant slot here. Next, I want to insert 46, so 46 can be inserted here, and you can see that there are no balance factors, imbalance values here. Okay, so you don't have to perform any rotation. Next, you want to insert 11, you can also insert 11 directly, there is no imbalance here. And then, yeah, and then 48. Okay, tell me, where should you insert 48? If you want to insert 48, where should you insert? You will be inserting it here. Okay, now when you insert here, there becomes an imbalance at this particular node. So first you need to perform a left rotation. So 46 goes to the root. So it will be something like this. I'll draw it here. 20, 10, you have 8 here, you have 15 here, you have 11 here, and then 50 here, 60 here, and here you have 46 with 32 and then 48. Now look at the balance factors. 0, this is 0, and this is 2, 1, which means 1. 0 here, here it is 1, left minus right, right is 0. So left minus right, right is 2, left is 1, minus 1. So 1, 2, 3, 1, 2, 3. So it is 0. Okay, so this is balanced even after inserting 48. You performed a LL rotation. Okay, so this is what happens if you are trying to perform rotation. This is for balancing your tree. This is for balancing your tree, right? Any doubts? Let me check the comments. Yeah, Devisri is also giving me a tip telling that mod of right subtree minus left subtree should be less than or equal to 1. Yeah, exactly. Right? Yeah, the rotation, Yashaswini, the rotation which we used last was LL. Maybe you are speaking about the previous rotation, right? So that is about the insertion and search operation in AVL tree. Now let us answer few questions. We have very few questions for AVL tree. All what you need to do is you need to understand what is AVL tree. And I didn't speak about deletion because it would not be sufficient to tell about deletion. That is the first thing, the reason why I didn't put deletion here. Secondly, no deletion questions were asked in most of the MCQs which I am dealing with, and I didn't include deletion into this, right? So can you please check with the answer for this one? An AVL tree is a self-balancing binary search tree in which the height of two child subtrees of any node differ by at least 1, at most 1, 2, at most 2. What is the answer? At most 1. Yeah. So we were talking about the balance factor should be at 1, plus 1, 0 or minus 1. And difference between them, so it should be at least 1 difference. So they are telling it's not left minus right or right minus left, difference. So at least 1 is the answer, right? What is an AVL tree? A tree which is balanced, a tree which is imbalanced, a tree with 3 children, a tree with at most three children. What is the answer? Simple question, right? So these are the questions which you get in your AVL tree. Kind of questions, right? Kind of. Yeah, the answer is AVL tree is balanced. A tree which is balanced. Okay? Right, next question. Yeah, you have some work here. Look at this. Which of the below diagram is following the AVL tree property? So if you want to know this, you need to write the balance factor of each. Okay, you need to calculate the balance factor of each. So look at 10. What is the balance factor of 10 here? 0. Balance factor of 11 is 1. Balance factor of 13 is 2. And balance factor of 2 is 0. Balance factor of 4 is 1. Balance factor of 8, 1, 2, 1, 2, 3. 3, 2 minus 3 is minus 1. But there is an imbalance here. Okay. But if you look here, if you look at the balance factors here, 0, 0, this is 0, this is 1, and 2, 2, which is nothing but 0. So this diagram follows AVL tree property. So it is only 2. Okay. Let me check how many gave me the right answers. Both. No, not both, because I have given you the explanation why it is not both. Okay, only 2. Right? Okay. So this I think we have seen yesterday. But binary search tree by using a post order sequence given below. So which one is the correct answer? So you know the post order. What is the in order? As it is binary search tree, the ascending order is the in order, right? So when you want to construct a binary tree, then you need two things, post order and in order, or you can take pre-order and in order to construct a tree, right? So, but in order is not given here. As it is a binary search tree, in order is nothing but the increasing order of, ascending order of these particular values. So, 2, 3, 4, 5, 7, 8, 9 is nothing but the in order. Okay. So, we have seen the in order of binary search is nothing but you'll be printing it in sorted order, right? So which one is the root? Post order, which means 5 is the root. Okay, so if you take 5 as the root, all these set will be to the left subtree and all these set would be available to the right subtree, right? So what is the next node? 8. So 8 is available to the right subtree, 8. So if you look here, 7 and 9 are on either side of 8. So you can directly draw here 7 and 9. And then what is the next node? It is 9 and 7. Don't worry about it. We have already only single nodes. So I have directly put 7 and 9. Next you have 3 here. So 3 comes here. So on either side of 3 you have 2 and 4. So 2 and 4. So what is the tree? Tree with 5, 3, 8, 3, 8. Yeah, this one, B. B is the right answer. Okay. So how many gave it right? Let me check. Yes, correct. Yeah, that's it I have for today. One more thing which I want to tell you. Firstly, which I want to tell you was about the trees. Okay. The complete tree, complete binary tree, and perfect binary tree, and what is that, full binary tree. Okay, so as per the instructions which I gave you, try to do it as per the instructions. If there is a concept of perfect, only then look at the concept of perfect. If there is no concept of perfect, only jump with complete and full. Only try to recall complete and full, right? Don't jump into perfect binary tree. Only if there is a concept, because I have seen MCQs which were giving bits on perfect binary tree. Okay, so it is better you know the concept of both and apply it only if it is required, right? That is the first thing. Secondly, regarding level, height and depth, you can say almost they are same, but as per the standard textbooks which I have referred, level starts with 1 and height and depth starts with 0. Okay, but it can be all same at times, it can be all same, but with respect to the question you can go ahead with what you are trying to take, right? So I hope you have enjoyed the session or at least learned something from the session. Maybe few were trying to ask me about writing the code, but you can assume that writing code for binary search tree, AVL tree in just 1.5 hours along with the MCQs, do you think it is possible? I don't think it is, right? So if you need a special session, go request for it. We will definitely have a session if you want something like that. Okay, so that's it. You can have a great good night. Have a great time. Thank you so much for attending this session. If you have any questions, you can put it in the chat box. I'm happy to answer. Yeah, I'll wait for 2 more minutes so that if you have any questions, I can answer it. So others, if you don't have any question, you can leave the session. No issues. Yeah, there's a question. Right. Good night, Saita. Yeah, I hope I'm done. So no more questions. So I'll leave the session. Thank you so much.